So yeah, we are very happy to have Esa. So Esa Ollila is a professor at Aalto University in Finland in a group of statistical signal processing. And this seminar is also a good start for the collaboration between DATAIA and FCAI, the Finnish Center for AI. I think it's the first seminar with no, not the first seminar with a Finnish presenter, but it continued this collaboration. So I'm very happy, and Esa, so I will let you present your work in signal processing and machine learning with on a particular topic of linear pooling of covariance matrices, right?
Yes. Yes. Okay, thank you. So during my talk, I will stop my sharing of my video, and let's try it. So can you see the PDF now? Fine. Yes?
Yes.
Yes. Yes. Okay. So thank you for this invitation. I'm very happy to give this talk, and first I would like to thank the co-authors of this work. So this is mainly the work of Elias Raninen, who is also here. He's a doctoral student in my group. And then these old guys, so myself and Dave, we are just enjoying the ride. And if you have really tough questions, I will just direct those to Elias. Okay, so let's look at the menu that we have here. So we have basically 6 items in the menu. So first, the introduction. So let's set up the notations. So I'm dealing with the problem that we have k classes, and from each population or class we have nk observations. And the problem is that we want to estimate the covariance matrix of each of the classes. And this covariance matrix is denoted by sigma k. And I would like to remind you that the covariance matrix is a symmetric matrix, and it's a positive definite matrix. So we have basically the problem of estimating k covariance matrices. And probably you all know that the most commonly used estimate is the sample covariance matrix, and it's given here. So I denote it by SK. So please recall this notation, because you will see these notations often. Sometimes when you have k populations, you may do some assumptions, such as you may assume that these populations share the same covariance matrix. And in this case, the commonly used estimate is the pooled sample covariance matrix. So it's basically just a weighted mean of the sample covariance matrices. And as you can see, and this estimator just weighs the sample covariance matrix by proportional weight is proportional to the number of observations in that class. And this estimator is unbiased of the common covariance matrix sigma. And so we are dealing in this talk, we are facing the challenges that we have very high dimensions. So P is the number of variables in each population. And we may end up having cases that actually the dimensionality is larger than the sample size. Or we can have problems also that we have many populations. And there are some applications where actually this may happen. Is, for example, if the population is, let's just say, measurements on a cancer, and there are several different classes of cancer, then each population or class of cancer can be divided into subclasses. And then these subclasses would have similar correlations or similar correlation structure, but slightly different. And then you would end up having a large number of different populations. And of course, what is also common in the academic literature, at least, is to assume that you have a Gaussian data. And in this talk, we assume that we have data that is not necessarily Gaussian, but can be generated from a larger class of distributions, and this distribution is the elliptically symmetric distributions. So when you face a problem of high dimensionality, you usually use an approach called regularization. And the commonly used estimator in this case is to use the regularized sample covariance matrix, which is then just a linear combination of the sample covariance matrix of the class and then a target matrix. And this target matrix is at least a positive semi-definite matrix. And then, of course, you have the problem of how do you choose those weights, alpha and beta. And these weights are, of course, different for each k. And first of all, if you would, the main problem is then that if you have a certain a priori knowledge, which is kind of reflected in this target matrix, that how would you choose these weights? And there are at least 5 commonly used criterions, and 3, or the first 3 are such that they minimize a criterion function. And perhaps one commonly used is the mean squared error. So you find those weights such that this mean squared error is minimized. Or you can use a metric. So, for example, you can use a Frobenius metric. You can use a Kullback-Leibler metric, which is kind of also called Stein's laws. You can use Riemannian distance. And of course, in machine learning, also cross-validation is commonly used approach to choose any regularization parameters. And then there are also, you can come up with this estimator also using Bayesian approach. And then that would be a totally different approach. Or you can also use the likelihood approach, which is also common, so expected likelihood approach. And so there are basically like 5 approaches that are commonly used in the literature to choose these weights. And in this talk, we are going to target the first one, so the minimum. We're going to minimize the mean squared error. And then, so once we have selected a criterion, then also the question is that, what about which target do you want to use? And perhaps easiest choice is just to use the identity matrix, because this would guarantee that even if the dimension is high and the sample size is small, then the estimator would be positive definite. And this another approach is to use a scaled version of the identity matrix, and then just take the other term alpha to be just 1 minus beta. And this would guarantee that the scale of the sample covariance matrix, so this regularized version will have the same scale as the sample covariance matrix. And then, so you basically wouldn't touch the underlying scale of the data. And this is also a very popular approach in the literature. And then the third approach is more taking into account the fact that we should take the knowledge from the other classes as well when we estimate the covariance matrix of the kth population. So one idea proposed by Friedman in 1989 was to shrink the sample covariance matrix towards the pooled estimate. And then this would kind of say that it's better to take into account that you can use the knowledge of the correlations in the other populations and then just smartly shrink this estimator towards this pooled sample covariance matrix. Then there are other approaches where you just say that due to the underlying application that you are working with, you have some knowledge of how the underlying covariance matrix will look like. So, for example, in finance literature, people use the fact that the covariance matrix is kind of like a factor, can be described by a factor model, and in fact even by a single factor model, where this single factor is kind of a market factor. So you basically, if you can estimate that factor matrix well, then you can shrink towards that matrix. Another idea also coming from finance is that, let's just say, if your data is stock returns or net returns from stocks, then if your portfolio contains only stocks from certain class, let's just say oil, then these stocks would be highly positively correlated and they would have similar correlation structure. So then you may want to pool towards a constant correlation matrix. Then in signal processing, especially in sensor array processing, there's an approach where you need to estimate noise and clutter covariance matrix. And you may have, due to the previous measurements, you may have some knowledge of how this noise and clutter covariance matrix is. And you may want to combine this previous knowledge with the current estimate of the covariance matrix. And this is an approach that has been developed in array processing. Then more in stats. Yes? Hello? Do you have a question?
I think it was just a bug. You can continue.
Okay, so then there's banded. You can use generalized banded matrices as proposed in this paper. So those are the kind of approaches that you can use for example, choosing the target matrix. And then there's another type of framework that has been proposed in the literature, and that's kind of using double shrinkage. And this is the approach that was proposed by Friedman, that you first pool your sample covariance matrix to or actually you shrink it towards that pooled sample covariance matrix. And then you do another step where you shrink that estimate that you got towards identity matrix. And the second step is kind of necessary to guarantee that your estimator is positive definite. And this is an approach that I would call double shrinkage. And there are other versions of this also. And Friedman originally used same shrinkage parameters for each class, and then a leave one out cross-validation for choosing these shrinkage parameters. And later in this paper, we proposed different shrinkage parameters for each class, and then a data adaptive tuning for these parameters. So, but now let's talk what this talk is about. So this talk is basically as follows. So we take as an estimator of the kth class, we just say that it's a linear combination of these sample covariance matrices. Then for each class, we find these weight terms, AIs, by minimizing the mean squared error. And this is actually the same thing as saying that we find this weight matrix A such that we minimize the total mean squared error. So the sum of the mean squared error of these. And if you could find this weight vector AK star, then ideally you would just plug it into this formula here as a weight and use that as your estimator. But of course this is not possible. In practice you would just need to estimate that and then plug it into the weight and use that as your estimator of the sample covariance matrix. And this, let's just say in a nutshell, this is what we are doing in the paper. So actually you can kind of describe our method with this single slide, but there's a lot of complex stuff going on, and I will explain it in the following slides. So I know that not all of you may be so much interested in covariance matrix estimation, but I want to remind you that it's actually a very crucial step in almost all machine learning and signal processing, because you need it commonly. If you do PCA, you need it if you want to do classification, especially certain type of classifiers like linear or quadratic discriminant analysis require an estimate of the covariance matrix. In fact, all of you who work in signal processing are very familiar with array processing techniques, and all these methods require to estimate the covariance matrix. Then if you work in statistics or machine learning, you may use graphical models. You need to estimate the inverse of the covariance matrix. Or in finance, there's also a large bulk of papers on covariance matrix estimation in finance. So there's actually, what I like about this topic is that there are so many different views on this problem, all coming from different angles, from different fields. And one field that we have been recently looking at is computer vision, pedestrian detection, because there you kind of build feature vector, and from a pixel, and from these 8-dimensional feature vector you compute a covariance descriptor based on a region that you choose from the image. And these covariances that you compute, you take the correlation matrix, but these correlation or covariance descriptors that you have will have some useful invariance properties. They are not so sensible to illumination conditions, and so that's why they are very useful for computer vision applications. So your covariance descriptors are features that you use and you give them to a machine learning algorithm. And we have a recent paper that kind of give an overview of these methods and how to use these covariance matrices in the following paper here. So there are plenty of applications of covariance matrices, and you can basically use these methods that I mentioned here in your favorite application. So let's talk about what this estimator is about. So before we move on, let me introduce some notation. So delta K I will use to denote the mean squared error of the sample covariance matrix Sk. And remember, sigma K is the true covariance matrix. And then I just build a diagonal matrix delta from these mean squared errors. And then I take the inner products of these covariance matrices, sigma I and sigma j, and make a symmetric matrix C out of them. And so this is all these elements are positive, and they are this is a symmetric matrix. So first result is that when you look at the mean squared error, it actually becomes, so we have this linear combination of the sample covariance matrices. When you look at the mean squared error with respect to, so the distance of this combination toward with the kth covariance matrix, then this problem becomes a strictly convex quadratic function in A. So it means, first of all, that we can have an analytical solution to this if we don't have any constraints. So what LINPOOL estimator that we look at is the following. So we construct the estimates of these parameter matrices, delta and C, and then we solve first the unconstrained problem because it has an analytical solution. And if it happens that one of these weight terms are negative, then we look at the QP solver for the problem so that we minimize the mean squared error, or actually the estimate of the mean squared error subject to the constraint that the weights needs to be non-negative. So once we have those weights, we just use them to build up the linearly combined estimator of the sample covariance matrices, and we do that for each class, so for each K. So that is very simply the method that we use to estimate the covariance matrix of each class. And I think it's useful to look at very special cases. So the first special case is that what about if we just have a single class instead of having like multiple classes? Then the estimator that we are looking at is just a scaled version of the sample covariance matrix. And in this case, if you look at this solution here, it was delta plus C, its inverse times the C, and C now is just this trace of the covariance matrix squared, and delta 1 was just the mean squared error of the sample covariance matrix. So as you can see, the weight that we have, the minimum is always between 0 and 1. And actually, it's easy to show that the mean squared error of this estimator, where you just scale the sample covariance matrix by this A1 star, is just the mean squared error of the sample covariance matrix itself times that constant. And this implies that this estimator, this LINPOOL estimator, is always more efficient than the sample covariance matrix itself. Then what about if we go further and assume that the data, the population that our observations are coming are Gaussian? So this means that the sample covariance matrix, or the scaled version of it, has a Wishart distribution. And we can use the properties of Wishart distribution and to say that the mean squared error of the sample covariance matrix is of the following form. And now what I can do is I can plug this into this formula here that you see. And once I plug it in, I can simplify the expressions, and what I get is A1 star is looking like this. So N1 was the observations from the class 1, and this gamma here is a measure of sphericity. And so this is for Gaussian data. So this would mean that the LINPOOL estimator for Gaussian data would be kind of, in a single class case, would be just looking like this. And here we would only need to estimate the sphericity measure to find that constant. So this was a single class case. So let's look at another example. So what happens if we have equal covariance matrices? So what about if I assume that all the class covariance matrices are equal, they share the same covariance matrix, which I denote by sigma? Then I can build these matrices C and delta. So now the C matrix is just, because the covariance matrices are equal, this just contains the inner products between the covariance matrices. So this will be just a matrix of 1 scaled by the trace of sigma squared divided by P. And then I can compute the analytical formula for this optimal weight. And this analytical formula shows me that each weight is proportional to the inverse of the mean squared error of the sample covariance matrix of the each class. So this is quite natural that you kind of, if the mean squared error of that sample covariance matrix is large, then the weight that we used in this is going to be small. So we don't kind of take that particular sample covariance matrix will not have a large effect on the estimator. So this is quite natural. And also we notice that all the weights vectors will be the same. So then what about if all the data is coming from Gaussian distributions? What about if all the populations are Gaussian? Then we again know that the sample covariance matrices will have Wishart distribution, so they will have the mean squared error of the Wishart matrix is known. I mean, this mean squared error of the sample covariance matrix is of the following form, and now I can plug these into this formula, and I can find a more explicit expression for these weights. And what is useful to note here is that each weight, remember that the pooled sample covariance matrix has a weight where the weight is just equal to the observations in the class divided by the number of all observations. And these are clearly different. So this estimator is unbiased, but of course the estimator that we get here, we introduce some bias, but we gain in the mean squared error. So this is always the bias variance trade-off that we are used to see in many machine learning problems. So these were the two special cases just to give you some idea how these weights look like in certain cases. So now the question that remains is that, is the estimator that we are looking at always positive definite? And actually, it's not necessarily, and that's why we are not satisfied with that estimator, but we add another term, an identity matrix, and then we find an weights minimize the mean squared error. So, but the good thing is that the problem is still quadratic programming problem, and we can find the solution as earlier. So actually nothing is really changed, except that now we have k plus one dimensional vector, and these matrices, earlier we had delta and c, now we have c tilde and tilde delta, which are given here. So the whole approach is easy to apply also in this more general case where you have identity shrinkage added to it. So then we also look at some extensions and modifications of this method. So, well, the first modification is the following. So what about if I would say that it would be quite natural to say that all these weights should sum to 1, and this kind of problem or idea is sensible, especially in the cases where the true covariance matrices, they're similar scale. So it would mean that none of the populations would be measured on different units, for example, because then obviously they wouldn't have the same scale. But if these observations are on the same scale, it's quite natural to say that, let's just say that, why don't we just say that the weights should sum to 1? And then, since this is a quadratic problem, we can just add another linear constraint to it. And then we are looking at this problem. So then, this is one thing that one can easily use in our approach. Then another extension is that why don't we somehow directly make a positive semi-definite constraint to the problem? And the idea is that, first of all, this was, if we denote by matrix beta, B is that matrix C plus delta, then the mean squared error would be of the following form, and then we can write it in this form. And now we can use a basic approach from convex programming and express this problem such that using a semi-definite program, where we directly enforce that the linear combination is always positive semi-definite matrix. So then this is also one approach that, or extension of the approach that one can use. The fact is that, in fact, that this solution is also the solution of the previous problem if these weights are always positive. So if the weights are positive, then there's no difference in these solutions. Then another approach that we are looking at is a slightly different version of having multiple classes, is that you find in the literature is that you have a single class only, but you pool your estimator not just to a one target matrix, but towards, or you kind of find a linear combination of your sample covariance matrix and a set of target matrices. And so if we have a single class covariance matrix estimation problem, so we have a set of target matrices, and these target matrices are positive semi-definite. matrices, we can look at a multi-target regularized sample covariance matrix estimator. And then this would be just a linear combination of the sample covariance matrix itself and these target matrices. Then, of course, the question is again that how should we choose these optimal weight terms? And the problem that may appear when we minimize the mean squared error is that these target matrices in practice, as you noticed, are not really independent of the data itself, because often they are built on a priori knowledge of the covariance matrix. So let's just say that the target matrix could be a single factor matrix model for stock returns, but you still need to estimate that those factors from the data itself, and these target matrices would not be really independent of the S1. So this may cause some problems, and that's why we propose a slightly modified version, which we call multitarget LINPOOL estimator, that given these target matrices, and it's good to remember that these target matrices, if they are estimated from the data, are kind of already have some error in it. So we can generate samples from multinormal distribution that have these structure, same covariance matrix structure as these target matrix, and then we just compute the sample covariance matrix from this data. And once we have these sample covariance matrices, we can just use the LINPOOL estimator that I described to you earlier, and just compute those weights as if those data, all these different sample covariance matrices are kind of coming from independent populations. And in that case, you can kind of assume that the weight vectors that we compute are somehow reflecting or are minimizing the mean squared error of the case where the data are independent between the classes. So this gives us another estimator, which is a slight modification of our original multiple classes problem, and this is called multitarget LINPOOL estimator. And I will show you that this is also very useful later on. Then, since we work in signal processing, the first question is that does this work for complex valued data? For example, in sensor array processing, we are dealing actually not with real valued data, but with complex valued data. And the answer is that yes, it will work. So everything that I just explained in the previous slide, previous slides will accommodate complex valued data. So you can plug your sample covariance matrix, which is for complex valued observations, and everything this goes as similarly. And the only thing that is actually affected is how you estimate these inner products and the mean squared error. Because obviously the formula for mean squared error of this matrix is slightly different when the observations are, for example, coming from complex Gaussian, or are they coming from real Gaussian distribution. So that is the only thing that you need to take into account. So far, I was just explaining that we have some estimates of these matrices, C and delta. And now I will talk what is our approach of estimating those matrices. So now I'm showing you the formulas that we need to find estimates of. So first of all, delta was a diagonal matrix of mean squared errors of the sample covariance matrices, and C was a matrix of inner product between the true covariance matrices. And what we do to find these estimates is we make an assumption that these populations have elliptical distributions, but we don't specify from which elliptical distribution these samples are coming from. So even the classes may have a different population. So let's distribution. So for example, first class could have a multinormal distribution. The second population can have a multivariate t distribution, and so on. So the only assumption is that we assume that the data itself has generated from elliptically symmetric distribution. And elliptically symmetric distribution, the PDF is given here for the real valued case. So sigma, so I'm assuming fourth order moments are finite, and this sigma here can be taken to be the covariance matrix of the random vector x. And this G is the density generator, and if we take the following form of the density generator, then this distribution will have a multinormal distribution. But if you take some different density generator, you can have a multivariate t distribution, you can have a generalized Gaussian distribution, and so on. So this class is general, and it contains most distributions that are commonly used in multivariate analysis. And if you have complex observations, then you have also an analog called complex elliptically symmetric distribution, which has very similar form as shown here. So let's first talk about how do we estimate the mean squared error of the sample covariance matrices. So to explain how the mean squared error looks like, we need actually only 3 scalar valued parameters. And the first parameter is the sphericity parameter. And this parameter is always in the range of 1 and p is the dimension. And if the covariance matrix is identity, so then you get sphericity is equal to 1. If we also need the scale, which is just the sum, actually the mean of the eigenvalues of the covariance matrix. Then the third scalar parameter that we need depends on the distribution, on the underlying elliptical distribution. So for example, it's called elliptical kurtosis, and it's only a scaled version of the marginal kurtosis of the elliptically symmetric random vector. So for example, if I would have a priori knowledge that my data is from multinormal distribution, then this kurtosis parameter would be equal to 0. So what we show is that, in our previous work, we already showed the real valued case, and we can easily derive the complex case also. And as you can see, the mean squared error depends only on these 3 parameters, so the kurtosis, and then the sphericity, and then the scale. And the scale is here as a multiplier of this other term. So once you have those estimates, you can have a good estimate of these delta scalars. So the first 2 are quite easy to estimate. We don't have to pay too much attention to those, but the sphericity term takes a little bit more attention because it's quite important parameter in this expression of the mean squared error. And so let me explain what is our estimate of sphericity. So first I would like to define a normalized covariance matrix, which I just call a shape matrix. And this shape matrix is denoted by lambda k. And then as an estimator of this shape matrix, so this k means that it's a kth class. And I use the following version, which is called scaled spatial sign covariance matrix. So it only differs from the sign covariance matrix in the sense that it has been scaled by the dimension p. Okay, so this will be our estimate of shape matrix. And what we show is that you can build a an asymptotically unbiased estimator of the sphericity under quite general conditions. So this gamma hat k, so notice that, so this was basically the scaled version of the spatial sign covariance matrix. We just take the square of that and the trace of that. So this will be just the mean of the squared eigenvalues of the spatial sign covariance matrix. We subtract this term here and scale it, and that's our estimate. So it's rather easy to compute. And we then have some theoretical results that this is actually gives these results that this is actually an asymptotically unbiased estimator when p, so the dimension goes to infinity. So then we also use a slight correction term here, and this correction term comes from the fact that you are using the spatial median. So in the previous slide, we are centering the observations using the spatial median, and when you do that, you kind of need a correction factor so that this will be will take care of the fact that there's some bias terms due to this estimator of the mean. So now we have estimator of mean squared error, and now we just need to build an estimator of these inner products, so these constantCij's. And to do this, we use actually these lambda hat i's. So actually, if you look at how does these diagonal terms look like, they are just the sphericity of the ith class times the scale of the ith class to the power of 2. So we already have an estimate of the scale, and now we have also, as I explained previously, we have a good estimator in high dimension of the sphericity. So why don't we use that? So then we have the following estimate of the diagonal term. And then for the off-diagonal terms, we also want to use the fact that now we have very good estimator of sphericity or the shape matrix. Then why don't we just use that again to estimate these off-diagonal terms? So these will be our estimates of diagonal terms. So now we have built estimates of delta and c. So now we have method that we can actually use in practice to compute the linearly pooled sample covariance matrices. So I'm going to show you how this works in a small simulation study. So I have a dimension that is equal to 300. I have 4 classes, and for simplicity, I just assume that we have equal amount of observations from each class. And I generate the data from a d-distribution with 7 degrees of freedom. And then I have a different covariance matrix for each class. And the different covariance matrix has always an AR1 structure, but the scale may be, so the scale of the covariance matrix is different, slightly different, and the correlation structure, so the raw is the correlation of the AR process, and we have the following correlations. So the first class has smaller correlation, and the last class has the highest correlation between the variables. And now we compute the normalized mean squared error here. So we do a simulation study. We generate 1,000 trials, and we compute our LINPOOL estimator for each class, and we compute how different it is from the true covariance matrix in the metric used, so the Frobenius squared norm. And the results are shown soon. So we use this LINPOOL estimator, we compute our weights, and then we compare our estimator to a multi-target regularized sample covariance matrix estimator, where the target matrices are actually the sample covariance matrices. So what I mean by this is that the target matrices are the sample covariance matrices from other classes and the identity matrix. So actually this sigma tilde k will be equal to this LINPOOL estimator. The only difference is that it may have different weights. And I'm using the method proposed in this paper, which is called leave one out cross-validation method. So they proposed a criterion, cross-validation criterion, using the idea of leave one out cross-validation, and then they showed that there's a fast way to compute these weight terms here. So I'm comparing how our approach would compare to such approach, and I'm also comparing how these LINPOOL estimators compare with just using the sample covariance matrices. Okay, now I went to a wrong direction. Okay, so here is the result. So here on x-axis, you can see, so this is the mean squared error, the blue line, for the first estimator of the first class. So in the first class, the correlation parameter was equal to 0.3. And in the fourth class, it was 0.6. And what you can see is that this leave one out cross-validation method we are doing similar on this large, when we have a large number or relatively larger number of observations. But when the number of observations decrease, then this method starts to lose its consistency of estimating these weights. So you can see that in this regime, it starts to behave quite badly. Then if I'm looking at just the total normalized mean squared error, which was just the sum of the mean squared error of all the classes, then you can see the difference here. So this blue line is our estimator, and then this is the leave one out cross-validation method. So the difference is more in this regime where you have a small number of observations. Then what about if I would just compare our estimator against the sample covariance matrices? Well, the fact is that this normalized, the obtained values for the sample covariance matrices are about 100 times the values obtained for the LINPOOL estimator. So there's a huge difference. So if I'm looking at the same scale here on the left-hand side, our method would have kind of here at the bottom, all these lines here, these 4 lines would be just showing as a one line here at the bottom. So clearly, in this scenario, you wouldn't want to use sample covariance matrix to estimate the unknown covariance matrix, but you would like to use information from all classes and smartly pool these together to obtain estimator of the individual covariance matrix. Okay, so I'm hoping that this picture here motivates you that these estimators are useful, and you should use them when you have a problem where you need to estimate multiple covariance matrices from different classes. And of course, such problems arises in many scenarios, like in classification, in radar processing, in finance. And actually, the finance problem is the next application that I would like to show, that these methods actually work really well in this problem. So the scenario that we are looking is that we have P number of stocks, and then we have a weight term, which is the proportion of wealth that we are allocating to ith asset. And these weight terms sum to 1. And here, the the random vector R denotes the net returns of these P assets. And in the portfolio studies, you have two key statistics of the net return of your portfolio. And these are, of course, the mean return. So how much return do you get from your portfolio? And also how risky is your portfolio? And this risk is described by the variance of the net return of the portfolio. And one of the portfolio allocation methods is the minimum variance portfolio allocation strategy, where you basically choose your weights, so how much you allocate to each asset, by minimizing the risk. And of course, you have to recall the constraint that these weights should sum to 1. And what you have here is that this weight, the optimal weight, depends on the covariance matrix, or actually the inverse of the covariance matrix. And so you would need to estimate this sigma here. And then there's a lot of literature done on this in the finance. So I'm looking at the problem, or actually I'm testing our estimator on real stock data. So I have net returns of 50 stocks from Hang Seng Index in the period from 2016 to 2017, and then from 2010 to 2011. And these periods are quite different because this, as you recall, 2010 and 2011, we had a crisis in the stock market. So there's clearly more volatility here on this data here rather than in here. So we are using the sliding window method, which is quite commonly used in these kind of backtesting problems in the portfolio studies. So we use previous n days to estimate the covariance matrix and the weight for the portfolio. Then we compute portfolio returns for the following 20 days, and then we update the allocations, and again do this sliding window until we reach the end of the data. So what we do is we compare the multi-target linear pooling estimator, where we use two target matrices that are commonly used in finance. So the first target matrix is the single factor market index model, which was proposed by Leduc in 2003 paper. And the second target matrix is the constant correlation model that was proposed in their sequential paper by Leduc in 2004. And then we also look at the LINPOOL method that has a constraint. Remember that the LINPOOL estimator is a weighted sum of the sample covariance matrix and these target matrices. And we can also look at the constraint that these weights sum to 1. So we have two versions, the one that doesn't have this constraint and the one that does. And then we compare it, our method, to three very popular estimator in finance. So the first one is this regularized sample covariance matrix, which has just a single target. So this is actually the same method that was proposed in this 2003 paper. And then we compare it with this second method that was proposed in this 2004 paper. And then we compare it with a more recent approach, where you are using nonlinear shrinkage of eigenvalues. This was proposed by Leduc in 2020 paper. And what we see here is that we use the global minimum variance portfolio. And what you can see here is that the realized risk, so of course you minimize the risk, so you would like to see that the realized risks are small using your method of the covariance matrix estimation method. And this happens to be the case when we use our estimator. As you can see, the realized risks are smaller than using these other estimators. And this happens both in the case of, so actually this n here is the past window length that you are using to estimate the covariance matrix. So for example, in this, if n is 200, we are using 200 past historical returns to estimate the covariance matrix. And here we are using 300 of the past historical returns and so on. And then, as you can see that of course, this is a very crucial component in this model, because you wouldn't want to use too many observations from past historical returns, but you should somehow compromise not to use, in general, you would like to use enough, but not too many, because the very near past results returns are more kind of trustworthy of how the market is today than the old historical returns. So this method also works well in portfolio optimization problems, and then this is a kind of future result that we would like to explore more of different approaches of this linear pooling method in portfolio studies. So I think my time is reaching out. So what else? So if you got interested in this, I want to note that we have a paper on arXiv, but it doesn't, we are actually revising the paper according to the suggestions of the reviewers, and our current version is still under revision, and we will soon, hopefully soon, submit it to arXiv. So some of the results that I showed are not yet in this arXiv version that is available, but you can already take a look at it, and the main frame is there, and then we already have the MATLAB and Python codes for our method, so you can just go on and play with those. Earlier I mentioned a double shrinkage approach. We have a very recent paper on that, which you can also look. So it's on the same problem of multiple class, estimating covariance matrices of multiple classes. So you may be also interested to look at that. And you may also be interested of looking at robust methods, which are also available in this link here. So that's it. And here I have some references of the papers that I showed earlier. So I'm happy to, I don't know how much time we have, but I'm very happy to answer any questions that you may have.
Thank you, Esa, for this nice talk. So we have a couple of time for question. So please feel free either to raise your hand or to directly ask questions, since there are so many people. Yes?
Can I ask a question, please?
Yes, for sure.
I'm Christian Bongiorno from Central Supelec. It was very interesting, your talk. Indeed, it seems the mathematical background of something we are recently doing. Essentially, we are applying that on finance. I would like to have your comments on that. So essentially, we are bootstrapping the data matrix. From each bootstrapping scenario, we compute the correlation matrix, and we filter the correlation matrix according to a hierarchical clustering. That indeed there's a way to force a loading matrix that has a hierarchical structure. So from this estimator, then we average. And it seems we average all the scenario, filter the correlation matrix. And it seems indeed a linear pooling, as you described, with a constant factor. The result there were much outperform the nonlinear shrinkage and all the other estimator, especially when the sample size was small. However, we noticed that there is a bias in the eigenvalue distribution, and I wonder if your approach is a way to correct that.
Yes, so I don't have a clear answer to that, but yes, I think at least I feel that this approach works reasonably well for financial data, at least because data is somehow elliptical, but has a bit heavy tails. And also, it seems like some skewness that may be present in finance data is not so severe that this underlying assumption of ellipticity is quite good. So we are actually doing reasonably good estimation of all these parameters that are underlying this method, the LINPOOL method. And maybe in your bootstrap approach, which I was not quite didn't totally understand like how you compute it, but it's worth trying. So if you have, maybe privately we can share some thoughts about your approach and perhaps like how to accommodate this kind of method that I described here.
Sure. I would like to continue this discussion in the following days. Thanks.
Esa, thanks for the talk. I have a question. Can you go back to the slide in which you show the true estimator of the sphericity, kurtosis, and the scale?
Yes, here. It's this one here, the last one.
Yeah, I mean there was the one. My question was about the estimator for the kurtosis.
Kurtosis, yes.
Yeah. So this estimator, I mean, depends on the specific density generator or not. I mean,
no.
No. Okay.
So actually, we are using quite just the kurtosis is just the fourth moment divided by the second moment squared, basically. Yeah. And then scaled. But so we are actually using a kind of plug-in version. You can kind of think it's just a method of moments estimate of the.
Okay.
We are not using like anything super smart here, but we are using some bias correction factors in our estimate of kurtosis. That we are using.
Okay.
But nothing like. But otherwise, it is based on the sample moments. So the kind of usual estimate of kurtosis, but taking into account the fact that the kurtosis, because the estimate of the moments needs some bias correction, so those are included in our estimate. But I think you could do much better estimate of kurtosis if you would use something a little bit more robust. But we actually haven't used that yet. But maybe it's worthwhile to investigate.
Yeah, just to understand, yes, which is the impact of an error in the estimation of the kurtosis in the final estimator.
Yeah. So the good thing here is that this kurtosis is a marginal kurtosis, and when you have a very large dimension, we compute the marginal kurtosis of each variable, and then we average that.
Okay.
So this averaging has some effect of reducing the errors in the individual kurtosis estimate. So I think that helps a lot because the kurtosis measure is actually the scaled version of a marginal kurtosis, and these marginal kurtoses are the same for each variable. So you can average those, and that's what we do, and then that little bit reduces the effect of, as you very well are aware, the kurtosis is kind of fourth moment is always like there's a lot of error. So
okay, yeah. Thanks for the answer.
Yeah.
Any other questions?
Yes, maybe. Can you hear me?
Yes, perfect.
Okay. So first, thanks, Esa, for the talk. And I had a question. It was more about slide 18 or 19. I think when you have the several matrices, then you take the kind of the arithmetic mean of them. And did you think about the possibility to take another kind of mean, such as an harmonic one or thing like
that? Yes. Okay, so maybe do you mean, I think maybe you're referring to this pooled version, so the pooled sample covariance matrix. So for example, here you're kind of shrinking this estimator towards the arithmetic mean. or almost like the spool. So actually, we haven't tried any of those approaches where one would use kind of smarter version of the, like, let's just say harmonic mean or something.
Okay.
Something different. So I guess also one problem is that because we are computing the mean squared errors, it becomes more problematic to compute mean squared errors between, a simple linear sum of sample covariance matrices instead of harmonic mean. But I think it's maybe worth trying. But we haven't tried that.
Okay, because maybe if I'm not mistaken, like from a statistical point of view, I think that the arithmetic mean would correspond to Wishart distribution, while an harmonic one would correspond to an inverse Wishart distribution. Stuff like that.
Not totally sure, but yeah, maybe. So if you, we didn't really need the distribution of the mean here, but so if you assume that the populations are similar, so if they come from a same distribution, then I guess that is true. Yes.
Okay.
So I mean, if those populations have a common covariance matrix, then in that case, I think what you said is true.
Okay. Okay, well, thank you.
Okay, thank you, Florent. Other questions? So if there is no questions, we're going to thank once again Esa. So and we all hope to see you soon physically.
Yes.
I mean,
Yes,
for
thanks.
me it will be in the weekend probably. And let's remind to all participants, to all attendees that we are launching with this seminar a webinar series of seminars in machine learning and signal processing. So together with the Finnish Center of AI, and both Esa and myself are in charge of this new series of seminars. So we'd be very happy to welcome you for any presentation in the future. So probably the next talk should be in next February.